This is me running 50 million simulations on my MacBook Air on a Roblox game. But how did we get here? This is Kaiju Cats. This is Roblox's interview game that they decide which of these CS majors are we gonna hire. I played this game the first time at a recruiting event my college had, and I sucked. Like, I was really bad at this game. So an idea, what if I trained an AI to be able to beat this game? Mr. Bean! So basically how the game works is you're controlling 3 cats trying to get as many points as possible. And the cats are kind of like Godzilla cats where they jump around and destroy buildings, and you're trying to use arrows and other power-ups to be able to control the cats. However, there's some caveats where if the cats jump into the same square, they'll destroy each other and only one will be left. And also, if you don't get a cat in the bed, you're not going to get a multiplier that's going to increase the cat's points that it gets. Now, the first thing that I was wondering is, like, is this even possible? Or is this idea just going to be scrapped in one of those projects I never get to finish? So looking at the game, the first thing we have to ask ourselves is this even possible? If you're not familiar with what branching factor is, it's basically this concept in machine learning that describes how exponentially difficult a problem gets for each layer that you go through. Some games like Connect 4 are really easy and they've been completely solved because the branching factor is small enough that a computer is able to explore all possibilities and literally find moves that guarantee you to win no matter what your opponent chooses. When you start off chess, there might be something like 35 possible moves, but after that first move, then there's 35 moves that your opponent could respond to from that position, but there are 35 starting positions that you could have chosen. And thus at each level, you have 35 and then 35 off of those, 35 off of those, 35 off of those. When I was looking at it, this game has roughly 30 some tiles that you can place commands on, but there's about only 6 commands that you can use. And thus, like, the branching factor isn't that crazy, so other things just cost that keeps the amount of possibilities down that you can choose. However, there is something that makes this game actually more challenging than something like Connect 4 or chess, and that's randomization. So when you have a chessboard or a Connect 4 board, each time you start, pieces are arranged in the same way, but for Kaiju Cats, the game changes after every run, and that's something I didn't even know until I played it a bunch. Because unlike a lot of other reinforcement learning programs, you're not able to use caching or something like remembering what the best possible outcome is after doing pre-computation, and everything is going to be have to derive from scratch on the go. So that's going to use a lot more processing power than if we could kind of remember what the best moves are at the beginning. So ultimately, the way I decided to approach Kaiju Cats was using something called simulated annealing. And there's a lot of science behind it, and there's a whole Wikipedia article as well as a Georgia Tech article you can read about it. But long story short, we select random moves we want to do, and then from those random moves, we select more random moves to do, similar to the trees you saw in Connect 4 and chess. However, what we're going to end up doing is pruning moves that lead to bad outcomes, and we're going to keep randomly exploring those that lead to good outcomes. However, one of the good things about simulated annealing is because we can sometimes get stuck in paths that look good, things that get cats a lot of points, but not really the most amount of points, because it has something called random acceptance. And that's basically that on a random chance, it'll accept simulations that are worse because of the idea that sometimes you have to take a little bit of a step back to take 2 steps forward.
Oh my god, that's such a bad move, dude. You have to play bishop c7.
And that concept makes a lot of sense in other games too. Sometimes in chess, you might have to sacrifice a queen in order to win the entire game. Also known as the Botez Gambit.
Can you sack the queen?
Oh, he said the queen. I said the queen.
So in order for my machine learning algorithm to work, I need to be able to run through millions and millions of possibilities of the game. And that simply isn't possible in Roblox because the source code is not public, and manually being able to run it, I'd only get maybe 2 or 3 games within the 15-minute time period that they allow for each map. So I had to get creative. I ended up creating a complete simulation of the game on my own. I created a state machine to be able to track where cats were, and also created methods that did things to just apply turns and power-ups. And my idea was, if my state machine is perfect, given the same number of inputs I put in the map, as in my state machine, it should get the same result, right? Wrong. Apparently there was a lot of stuff I missed. Things such as, what happens if a cat hits a boulder? Does it go back, or does it lose a turn? Or things like, if a cat jumps on a building with a power-up, Are the points for the building added first and then the times 2 multiplier is applied? Or is the times 2 multiplier applied on the current points and then the bonus is added for the houses? And all of these edge cases were driving me absolutely crazy. But eventually I got something that matched the actual state of the game.
2 hours later.
Now it was time for the hard part, creating the machine learning algorithm.
2 hours later.
And so I coded up the most generic boilerplate version of simulated annealing, and here are the results. Not great. Because I first played this game in a room full of cracked GT kids, I knew that a score like this wasn't that good. I saw people score 140, 150,000 points, and so I knew those were levels that we could reach, and maybe even higher. I think the reason behind this is since our search tree was so large, even with simulated annealing, we can still sometimes get stuck in those points because the search span is just so massive. And so what I ended up doing is I ended up doing a few things. 1, adding random restarts in multiple places, and then 2, introducing something called multi-threading, which is basically using the full power of all my CPU cores. Scores here look not bad, but they still weren't good enough. So the final optimization I ended up adding, heuristic that rewards getting cats closer to the beds. And at this point, I'd play the game maybe 100 times myself, and I'd get scores that were pretty high up there, like 170, 180k. And in all of those solutions, I always maximized the value of the last cat entering the bed. And with that, we had solutions that were looking pretty good. Check out these sample runs. So Roblox actually has published some data about this study because they've used it in a mass number of interviews for candidates. And the actual mean score for candidates scoring this game is just 40 to 50k. So that means our algorithm was playing in one of the top percentiles of these candidates. And actually, I ended up getting a record score in this game that's never been achieved. I found that 215,000 is actually the ceiling for this game. You can't get higher. And no one so far as I've seen has ever gotten this score. And so ultimately, this algorithm was able to crush this interview game.